cranes and hooks and shackles or 5 or 6 muscular people to move that sow bar around. The little old pig iron things, I can take those and remelt them and make cast iron cooking utensils, or I can take them and I can forge them into nails or horseshoes or whatever. They still call it pig iron, okay? They don't usually talk about the sow bars anymore, but that's where it came from. That's where the term pig iron came from. Because and after they've let it solidify, 5 or 6 hours after they cast it, they would then just take the metal out of the mold of the sand, take it over to the forge shop, and then they would just rake the sand back and dig more holes for the next casting that's going to come. But after you get all the metal out, the next stuff that comes out is the slag. And they would basically block it off, and they'd have another trough over here, because the slag is a molten glass, less dense, and they would just form a bunch of slag, and the slag would just go to the dump. Okay? So there's all kinds of pollution up there by Saugus Iron Works for 10 or 15 years. And if you take another one of my classes, I talk about why they came to Saugus to make iron in 1630s. Because they were deforesting England. England was having an energy crisis. They had cut down all the trees. Okay? And so what did we have over here? The natural resource. You have limestone and sand all over the world. You have iron ore all over the world. What they had in America in 1620 was trees to make charcoal. Okay? See, it all sort of fits together. It all sort of makes sense historically. This has nothing to do with welding, though. Any other questions? It's okay. I like to tell the story. Okay. So I got this iron, and that actually started out as why is cast iron over here and why is steel over here. It's historical. Okay? But also cast iron melts at a lower temperature because of the eutectic. But I was talking about what you really like to have historically is something that you can harden. So I've got aluminum, and I didn't have a piece of hardenable aluminum in my office. This is a piece of aluminum. It happens to be 5454 aluminum plate. It's non-hardenable, but many aluminum alloys, most of the aircraft alloys, the aluminum copper that the Wright brothers used for their engine in their plane was an aluminum copper alloy. You heat it up. It has a phase diagram. Looks something like this. It doesn't have this lower part, but you heat it up to where you actually heat it up into a region over here. Put the copper into solution, quench it. Then after it's cooled down to room temperature, you heat it back up to an intermediate temperature, and you form these copper precipitates. And I remember 20 years ago, someone published a paper in Science. They'd gone to the Smithsonian, gotten a little sample from the Wright brothers aluminum engine, put it in the transmission electron microscope, and measured the size of the precipitates, which had been aging for 80 years or 90 years at the time. And they showed that they were consistent with an aging time of 90 years. The size of the precipitates had been coarsening and getting coarser over 90 years. And so they compared that with, a 3-hour aging and a 4-week aging and a 1-year aging, and they could plot it on the same log plot and show that it was consistent. And so with diffusion of copper and aluminum. So aluminum can be hardened, and I could have brought my baseball bat, but the highest strength aluminum alloys are actually baseball bats. They're not aircraft alloys, and they're precipitation hardened. Okay? So you can harden aluminum by quenching and tempering. You can harden steel by quenching and tempering. There are some stainless steels you can harden. We call them precipitation hardenable. What a clever name. We have copper alloys. This is my beryllium copper crescent wrench. Costs about $130. You can buy one yourself. Anyone remember from last term why we use beryllium copper tools? You can buy a whole tool set, all kinds of tools, $4,000 instead of $400 out of steel. Sparks. They use them in spark-free applications like mines, where you might have methane gas, and you don't want a spark that goes kaboom, okay? They're spark free. Why are they spark free? The thermal conductivity of copper alloys is much better. I can take two pieces of steel and bang them together, and I can make sparks. That's how Boy Scouts or Girl Scouts start fires, right? I can, if I do it with the right type of thing, I can generate enough frictional heat to get 1,000 degrees and start a spark. So that's one way to start a fire. You can't do it. You can try all day, but there's not thermal conductivity. You bang two pieces of beryllium copper together, you'll never get a spark. Okay? So, anyway, so they make all kinds of, that's the precipitation hardenable alloy. That's got well over a gigapascal strength. Okay? 150, 180 KSI, something in that range. Okay? So it's just as hard as a hardenable steel. Should have the good wear resistance just like a steel crescent wrench. But instead of a $10 crescent wrench, it's a $100 crescent wrench. Okay? So that's a little bit of basic metallurgy, but we do need to understand some basic metallurgy. Another piece of basic metallurgy that we need to understand is the difference between the word hardness and hardenability and hardening. Although hardening is not that important. But in any case, here's something out of a materials engineering dictionary. Let me find mine. Oh, it's over here. And I'll put it up on the board. And you can read it yourself, but actually I didn't intend Jerry to make 20 copies of this, but she did. In any case, well, let's do hardness first. Hardness is a measure of the resistance of a material to deformation. Is that what it says? To indentation or abrasion. Okay, so you can read it. You don't have to, I don't have to blow it up. So, clay, soft, not very hard. I can indent it with my thumb, right? I can even puncture it with my thumb. Anyway, that's hardness. And it turns out, I'm going to show you in a little bit, that hardness is a function of the carbon content in steels. Hardenability, on the other hand, is the depth to which I can harden something. Okay? It turns out hardenability is a function of the alloy content. We have carbon steels, and it turns out carbon steels, I can only harden carbon steels to, let's say, less than ½ inch deep. If I add a bunch of alloy to this, I can harden 10 inches deep. And all I'm doing with the alloy, if I add molybdenum to the steel, molybdenum likes to form carbides. Chromium likes to form carbides. Nickel doesn't, but nickel slows down the reaction other ways. But the transformation between the FCC that I'm going to try to quench in, and then I might precipitate by tempering it, is slowed down by all these alloying elements. Some of them tie up the carbon so the carbon can't move around. Some of them slow down the diffusion of the iron so the iron can't move around. So hardenability is a function of the alloy content. Hardness is a function of the carbon content. If I put all this together, hardness is a function of carbon, and hardenability is a function of the alloy content, and it's the depth of hardening. So if I'm making automobiles out of sheet metal, I can use carbon steels because the sheet metal is less than a ½ inch thick. If I'm making some big pressure vessel, I'm going to need to use some alloy content if I'm going to have a hardenable steel. Or if I'm building a nuclear submarine, here's a nuclear submarine steel, HY80, inch thick. It's got to have alloy content. It's got about 3% alloy content in it. It's got nickel, chrome, molybdenum in this steel for hardenability. Because it turns out if I take that iron carbon phase diagram and I quench it, I take it up here to the austenite and I quench it down here to the ferrite, very quickly I won't form a body-centered cubic crystal structure. I'll form a body-centered tetragonal crystal structure, which is known as martensite. And martensite is extremely hard. It's an athermal transformation, which means it occurs at the speed, near the speed of sound. Yeah.
So are you saying that low carbon steels are 4 inch?
Yeah, it'll be soft in the center after you quench and temper it. The high hardness, the martensite that you're going to form is only going to be probably, if it's low carbon steel, may only be 1/8 of an inch deep. It's going to be less than a ½ an inch. You can't get deep hardening in carbon steels. The reaction is too fast. Okay, I can show you how fast the reaction is. I just happen to have a book. This handy dandy book, which I actually had at home. I didn't have a copy in my office because I never use it. Okay, but this book is full of time temperature transformation diagrams for irons and steels. And you have to be a metallurgist to love these things. But here's a diagram showing steel that I'm going to heat up to it's 1200 degrees. I don't know if you can read that, but anyway, you don't have to learn these diagrams. This is called a time temperature transformation diagram. This is time, this is temperature, and this is the C-curve behavior for transformation of the steel. So I heat it up to 1300 degrees C, which is, or 900 degrees C, which is 1350 Fahrenheit or something, and I quench it. If I quench it fast enough, well, how fast is fast enough? This is time in seconds. I have to do it within less than a second or two in order to avoid it just transforming to ferrite. If I want to get martensite to get really hard steel, I got to do it really fast, unless I add alloying elements. Now, if I add alloying elements, I can add molybdenum. This is a molybdenum-free steel, and I have to transform it. You can't see the plot down here. It's probably on the very bottom here. It's 1 second, 10 seconds, 100 seconds. This is just a series of steels with 0 molybdenum. This is 0.15 molybdenum, 0.3, 0.38, and 0.5% molybdenum. And you can see how molybdenum is just changing the nose of that C-curve over from a second to 20 seconds. Okay? I can slow the reaction down by a factor of 20 by adding 0.5% molybdenum to the steel. Well, that does cost me a little bit. A 0.5% molybdenum is going to cost me $100 a ton. My $400 ton steel is now a $100 a ton steel. So the question was, why are there so many steels? Well, if you're buying 100,000 tons, you want just the right amount of alloy. You don't want to pay for a 0.5% moly if you can get by with 0.4 moly for the thickness that you're interested in. Okay? So that's why there's so many steels. It's used 1.5 billion tons a year in the world, and at that quantity and at these alloy prices, it's cost effective. Now, so we really will take 12 units on welding metallurgy if I don't even get to talk about welding in the first lecture. But, excuse me, I need a drink. But anyway, see, there's fewer bubbles, right? It's been an hour. There's still bubbles in there. If I shake it up, I can get some, see, there's still CO2 in there, right? I had to get some pressure waves to help nucleate some, okay? But there's still some stuff. There's still more CO2 to come out. but it's evolving a lot slower than when I first poured it in. And that is, believe it or not, this is the first time I've told people about this before, but this is the first time I've ever bothered to go out and buy a carafe and waste 3 glasses of Sprite. Not that it's a white. That's not really a waste. This stuff shouldn't be on the market. But anyway, but use 3 bottles of Sprite to show. Yeah. It's not 10 yet. It's not even 10:05. So cool it. Okay. So anyway.